turn on your camera and say hello.
Hi, Rebecca. Good to see you.
Hey, Luke. Hey, everybody.
How's everyone doing? Everyone still getting on Zoom webinars. It's great. I know we're all sort of in the process of transitioning back to the office, and it's brought a whole new kind of interesting phase of the pandemic or post-pandemic.
Definitely. And while people are joining and we're just chatting at the beginning here, if anybody has any thoughts on future in-person events, whether you'd be interested in that or whether the Zoom thing actually works better for you, let us know, because we'll probably be sending out some kind of poll about that in the next couple of months.
And I guess where we're sort of thinking is we'll keep doing at least some hybrid webinars to make it easy for people who want to learn more about embodied carbon but don't want to drive in LA traffic, and alternate that with some more in-person, more networking type happy hour events, sort of like every other month maybe. That's kind of what's in the back of our minds. With that, I'm gonna share screen. We'll go ahead and get going, and we have like a little bit of as always, have a little bit of a kind of brief intro just while people are trickling in. All right, Laura, can you see my screen?
Yep.
Okay. So welcome everyone. This is the CLF LA hub, talking this evening about the latest material innovations for both mass timber and concrete. Very excited to have Rushita and Rahul joining us and giving some great presentations this evening. We'll hear more from them in just a few minutes. Before we get going, so here's the hub instigators. If you see any of these names in the chat, you need anything, you have any questions, feel free to chat any of us. Hopefully, we also have a Slack that people can engage with. Some other kind of background or kind of housekeeping things. The last meeting we had was a 3 minutes of brilliance. Hopefully people got to see that. If you haven't seen it, it's up on the YouTube channel. One of the next CLF global events is gonna expand on those presentations. So we put a poll in the Slack to see which topics you'd be interested to hear more about. So check that out. And usually we like to start these events with some of the recent news. Here are just a couple articles that I've read recently and shared about the biggest concrete plant in Sweden getting shut down because of environmental concerns, and also the latest out of the EU from France about some of their embodied carbon measures. They have some pretty ambitious reduction targets and incorporating dynamic life cycle assessments and some of those things. And last bit of news is SE 2050 reached its goal of 50 signatory firms just this week, so that's pretty exciting. Is there any other news that anyone else cares to share or heard about? We won't linger too long on this, but if anyone cares to say anything, have at it. All right. So we also always want to start, just in case, it's still a pretty new topic. So the 60-second elevator pitch of what embodied carbon is, why it's important. Why it's important is buildings are the #1 contributor to global greenhouse gas emissions. And a lot of attention has been paid to kind of the efficiency of MEP systems and heating and ventilating those spaces. But just recently, there's been a lot more attention being given to the actual manufacturing of materials and those impacts, known as embodied carbon. It's the rest of the life cycle of the material because of its significant impact to the environment as well. So that's just the very high level background. Lots more content on our website, if clfla.org, if you are interested in learning more and need some more background content. But we want to give most of the evening here to our two presenters that we're really excited to hear from. Both are going to give about 20-25 minute presentations, and then we'll have time to discuss as a group this very exciting research. First up is Rushita. Rushita just finished her master's at USC. She was studying mass timber and early life cycle assessment. And I think we originally got connected through Sanjeev, which I think I saw Sanjeev on the call. Hopefully, shout out to him. Thank you for connecting us. It's really exciting research, and I'm looking forward to hearing more. So, Rushita, the floor is all yours.
Sure. I'll share my screen.
Luke, you might have to stop the share first. And just a note to everyone on the call, if you have any questions as the presentations are going, feel free to type them into the chat, and I'm going to collect them for the Q&A at the end.
Okay, great. Hi, everyone. I'm Rushita. I recently graduated from the University of Southern California with a Master of Building Science. And I'm currently working at AECOM New York as a high-performance building specialist. Today, I'm going to be talking about my graduate research that I did on the embodied carbon of wood construction. Now, with the need to decarbonize the built environment, it becomes important that we focus not just on the operational carbon, but also on the embodied carbon footprint of the building and find ways to mitigate it. One such way is to use low carbon materials. Wood is a naturally occurring low carbon material and has the ability to sequester carbon. This, along with its structural properties, makes it a good choice of material for low carbon construction. Now, wood is processed to create engineered timber, and different processes yield different products. This research focused mainly on the use of glulam and cross-laminated timber and their impacts on the embodied carbon footprint of the building. Now, talking about structures of a building, it is very important to decarbonize them because they are one of the highest contributors to the net embodied carbon footprint of the building. And so the availability of mass timber made it possible to build tall structures out of wood. A timber structural system can be broadly classified into two categories. An all timber structural system is one wherein timber is used to resist both the lateral as well as the vertical loads. Whereas a hybrid or a composite system is one wherein another material like a concrete core is used for the lateral loads and timber is used for the gravity loads. Now, to be able to reduce the embodied carbon of a building, it is important that it be assessed accurately first. So the impact of a building all throughout its life cycle is assessed using a life cycle assessment. This is classified into 5 stages depending on the stage of construction that you're addressing. Of all these 5 stages, the first stage, that is a product stage or the cradle to gate stage, has the highest impact on the embodied carbon footprint of the building. And so the tool that I used, which is the embodied carbon in construction calculator or the EC3 tool, supplements the LCA process by addressing this stage of the entire process. Now, moving on to my methodology comprised of 4 main steps. The first step was to build a building information model of the case studies. Material quantities from these models was then taken into the EC3 tool, wherein the materials were allotted EPDs, after which an embodied carbon analysis was carried out. And the final step was to compare and analyze different scenarios and different case studies to understand which structural system has a higher impact and which variables impact the carbon footprint of a building. So the research used 2 case studies. The first case study was the tall timber study of the DeWitt Chestnut Apartments. This building is an existing concrete structure in Chicago. As part of research by SOM, they redesigned it using mass timber products and derived a composite timber and an all timber structural system. This case study was used for 2 assessments. So the first analysis was done to understand how the use of the EC3 tool impacts the calculations for embodied carbon. And this was done by comparing the published embodied carbon results for the composite timber structure with those derived using the EC3 tool for the same structure. The second analysis was to compare and analyze the embodied carbon footprint of the composite timber and the all timber structural system. The second case study used was a location specific case study. And by this, I mean that the location of the building and the location of the manufacturing units of the materials was known for this case study. Now, this case study was important because timber as an industry is not global yet. And it is highly probable that to be able to build with timber in certain parts of the world, it may have to be transported from another country. So it becomes important to understand how transporting timber these long distances impacts the carbon footprint of the building and whether it still makes sense to use it as a construction material. So the case study over here is the Kanchenjunga apartment. This again is an existing concrete structure located in Mumbai, India. This was redesigned using CLT as part of a conference in India. So the location of the building is in India, whereas the location of the manufacturing unit for CLT is all the way in Japan. So moving on to the analysis, the first analysis was to see how the use of the EC3 tool impacts embodied carbon calculations. So the first step for the entire research was to build a building information model using Revit, which was done using published data. And so to ensure that the calculations were accurate and that the comparisons that were carried out were accurate, the accuracy of the Revit model had to be verified first. And so that was done by comparing the material quantities derived from the Revit model with those which were published in the report. And while doing so, a bit of a small discrepancy was noted in the concrete quantity, wherein the concrete was almost 24% higher in the Revit model. This was attributed to the fact that the concrete sections in the Revit model did not have RCC modeled into them due to lack of available data, and as a result of which the overall volume of concrete increased. Now, this difference in material quantity led me to my next step, which was to understand how a difference in the material quantities for the same structure impacts calculations on the EC3 tool. So the graph over here shows the embodied carbon results for 3 different material quantities. The black is when the report quantities were used. The yellow is when the Revit material quantities were used. And the blue is where a quantity between the two was used. Now, looking at the overall embodied carbon footprint, the carbon footprint of the model from the model quantities was higher due to its increased concrete volume. However, the difference in both the embodied carbon results, that is for the report and the Revit material quantities, was not much. It was only by 9%. So this assessment was basically highlights that the EC3 tool can be used for early stage assessments where you do not have very accurate material quantity information. However, ideal results, an ideal use for the tool would be when precise quantities are known. So the next step was to see how the EC3 tool impacts the calculations of embodied carbon. So the EC3 tool uses product-specific EPDs, which is environmental product declarations, for calculating the embodied carbon, whereas the published results used industry averages for calculating the embodied carbon. So to see how these EPDs performed against the industry average, a range of EPDs was considered on the EC3 tool and the calculations were carried out for all these EPDs. So the graph over here shows the embodied carbon impact for 3 different scenarios. The black is the embodied carbon footprint for the existing concrete structure. The blue is the published embodied carbon result for the composite timber structure, which was carried out using industry averages. And the yellow is the embodied carbon results derived using the EC3 tool, which was carried out using EPDs. Now, the top graph is a situation where high embodied carbon product EPDs were allotted to the materials on the EC3 tool, and the bottom graph is where low embodied carbon product EPDs were allotted. Now, from the top graph, it can be seen that all the materials that were assessed using the EC3 tool have a higher impact than the industry averages or the published results. Whereas on the bottom graph, it can be seen that all the materials have a lower impact. Now, this assessment over here shows that the industry average may not always provide a very accurate and a very clear picture, as it is probable that the product that is eventually assigned to the material may perform worse than the assigned industry average, which can lead to inaccurate and misleading results. Now, secondly, and more importantly, the main difference in these two methods is how they report the embodied carbon for timber. The published embodied carbon results for timber have a net negative value, whereas the EC3 tool gives a positive value. This is because the published results accounted for the carbon that is sequestered by wood, whereas the EC3 tool, due to its system boundaries, does not account for carbon sequestration. So the next step was to see, the next step was to see how the timber would perform had the carbon sequestered not been accounted for. And so for this assessment, two different carbon sequestration values were considered, one wherein the end of life treatment emissions were accounted for, and one where they were not. Now, when you use two different carbon sequestration values, the end results are distinctly different. This assessment again highlights that in the absence of information about the end of life treatment emissions and carbon sequestration, the use of a more conservative tool like the EC3 tool avoids misleading and inaccurate calculations. Now, the second analysis was to compare the embodied carbon of the composite and the all timber structure. The graph over here shows the embodied carbon footprint of the composite timber structure in black and that of the all timber structure in blue. From the graph, it can be seen that overall for the whole building, the all timber structure has a lower embodied carbon footprint than the composite timber structure by almost 17%, even when carbon sequestration is not accounted for. However, 17% is not a very big reduction. And so it asks the question that whether such a small reduction justifies the organizational rigidity that would arise when you have to use an all timber structural system. Now, this assessment over here was carried out without accounting for carbon sequestration. So another assessment was carried out after that to see how the carbon footprint changes when you start including the carbon that is sequestered by wood. Now, the graph over here shows the all timber structure with carbon sequestration in yellow and the composite timber structure with carbon sequestration in red. Now, when you start accounting for the carbon that is sequestered by wood, the carbon footprint of the building changes dramatically. Both the structures now have a net negative embodied carbon footprint, which means that they now remove more carbon from the environment than release into it. Furthermore, it also changes how timber contributes towards the net carbon footprint of the building. Now, in the scenario where where carbon sequestration is not accounted for, it can be seen that timber is one of the highest contributors to the net embodied carbon footprint of the building from the graphs on the right. Whereas when you start accounting for the carbon that is sequestered, timber actually contributes towards a net reduction of the carbon footprint of the building. So this assessment highlights the importance of carbon sequestration, which further highlights the importance of sustainable forestry practices so as to avoid carbon sink deficits, to use the ability of wood to sequester carbon and justify the use of timber as a sustainable material. The last analysis was for the location-specific analysis, where the building was in Mumbai, India, and the location of the CLT manufacturing unit was all the way in Japan. Now, the first assessment for this analysis was done assuming that the location of the building and the location of the manufacturing units is the same. For this analysis, two different values of embodied carbon were used for the CLT. This is because the CLT to be used would be transported from Japan, would be manufactured in Japan. So a value that matches the embodied carbon of timber that is manufactured in Japan based on their LCA studies had to be found. However, a close enough value could not be found on the EC3 tool, and as a result of which, two different values were considered to carry out the calculations. For either of the cases, the CLT structure has a lower embodied carbon footprint than the existing concrete structure, even in the scenario where you do not account for carbon sequestration. This assessment, however, highlights a limitation of the EC3 tool and its limited database and how it limits its use when EPDs of products that are not sourced within its database need to be used. So the second assessment was done to account for the transportation emissions associated with transporting timber over 9,000 kilometers by sea and by road from Japan to Mumbai. Now, when you start accounting for the carbon associated with transporting the timber, there is a significant increase in the carbon footprint of the CLT structure, which is shown in yellow. The carbon footprint increases by almost 36%, which is a significant increase in from had it been sourced locally. However, despite this increase in the carbon footprint of the building still performs better than the concrete structure, which was built using locally sourced but conventional materials. So this assessment over here highlights the importance of including transportation emissions, as they do have a significant impact on the embodied carbon footprint of the building. Furthermore, it also says that for this particular case study, that is when the building is in Mumbai, India, and the manufacturing unit is in Japan, it does make sense to build the structure out of timber and continue to have a lower carbon footprint. But this is a very location-specific case study and a location-specific analysis, and would change with the change in the location of the building, in the location of the manufacturing units, and in the mode of transportation. So basically, this assessment should be carried out for every analysis or every building that uses timber that is not locally sourced. The last assessment was done to include carbon sequestration because Japan has laws and policies in place to ensure sustainable forestry practices. Now, again, when you start accounting for the carbon that is sequestered by wood, the buildings start to have a net negative embodied carbon footprint and remove more carbon than release into the environment. This assessment further highlights the importance of sustainable forestry practices and the importance of carbon sequestration. So to conclude, the EC3 tool does provide a more accurate value as it uses manufacturer EPDs rather than industry averages. It does not account for transportation emissions and carbon sequestration, but provides a conservative analysis when accurate information about forestry practices and end-of-life treatment emissions is not known. Between the composite timber and the all timber structure, the all timber structure performed better in terms of its embodied carbon footprint, even when carbon sequestration was not accounted for. When carbon sequestration was accounted for, the structure started to have a net negative embodied carbon footprint, which meant that they removed more carbon from the environment than released into it. The inclusion of carbon sequestration is important, which further more focuses on the importance of sustainable forestry practices. Lastly, transporting timber long distances does have a significant impact on the net embodied carbon footprint of the building. However, in the case of, in this particular case study, transporting the timber still made the CLT structure have a lower carbon footprint as compared to the concrete structure. But again, to reiterate, this is a location-specific case study, and the analysis would change with the change in the location of the building, in the change in the location of the manufacturing units and the modes of transportation. That's about it. Thank you.
That was really great. Thanks so much, Rushita.
No problem.
Yeah, lots to dive into there. And I mean, I think it really speaks to the importance, especially on the life cycle assessment stuff, of where we draw our boundaries and what we're considering.
Yeah.
Thank you for beginning the conversation there. Lots of questions, but we'll leave it till later and we'll.
Okay, I'm just going to stop sharing my screen now.
Perfect. We'll transition to Rahul. And while Rahul's getting started here, I'll just give him a very brief introduction. He's going to be presenting on some research coming out of UCLA about a different kind of sequestration, dissimilar from the timber growing carbon. This some really interesting research coming out about sequestering carbon into concrete, and congratulations to you, Rahul, as well, because you recently, you and your team recently won the X Prize for this challenge too. So really excited to hear you speak to it and learn more about it.
Awesome. Yeah, thanks. Good afternoon, everyone. Thanks for the invitation. We've been looking forward to engaging with Carbon Leadership Forum for some time, so it's definitely great to kick that off with our home chapter. I'm going to approach this less from the academic sense. We've now spun the effort out into a private company, so hopefully you don't mind getting the sort of pitch from that angle. But I think in either way, you'll hopefully get a better sense for what we're doing, and hope this is the start of many discussions. So let me just make sure everyone can see the screen. All right, perfect.
Got it.
So before I tell you what we do, let me just set the stage in terms of our motivations a bit. So I think everyone on the call is aware of concrete's massive carbon impact and our need to find solutions. Ideally, we do that at the front end of this massive increase in global building stock that will be taking place over the next few decades. Fixing this problem at the cement plant is a tough order, right? There's many things you can do at a cement plant that are incremental, but anything that's substantial in terms of decarbonization is frankly hugely capital intensive. And that means it's very, very tough to implement without broad government intervention. And frankly, I'm done holding my breath waiting for that. So, alternatively, the other thing we can do is try to solve this problem where concrete is made rather than where cement is made, by moving away from Portland cement towards lower carbon input materials that cure or harden by reacting with carbon dioxide. And this is particularly amenable for the 30, 35, maybe 40% of the market that is precast. And obviously precast is a growing segment of the overall concrete marketplace. So historically, attempts to use this approach to make substantial improvements in carbon footprint of concrete have been characterized twofold. One, by expensive or scale limited materials. And then second, by expensive curing processes that have required concentrated CO2 delivered at high temperature and high pressure. And when you put all that together, it means that the end product is very, very expensive. And fundamentally, that's why these solutions haven't gone anywhere. Concrete, in the end of the day, is a commodity. So at CarbonBuilt, what we are doing is turning dilute CO2, sort of cheap CO2 from a wide variety of emission sources, into low-cost, no-compromise precast concrete. Okay, we do this first by making a change on the formulation side, and that involves substituting most of the Portland cement with a range of widely available and mostly waste materials. Okay, when cured with CO2, and it's a substantial amounts of CO2, we can meet concrete's performance requirements while substantially reducing the carbon footprint. And that reduction happens in two ways. The first is that on the embodied carbon side of the materials that are being used. So we're reducing cement usage by something on the order of 60 to 80%, particularly in the cases where all the substitutes are waste materials. We get a big reduction we get a reduction in any case, but it can be a quite substantial reduction in the embodied carbon. And then we're using CO2 to cure the product. So CO2 is reacting with some of these materials to form other materials that harden. And so you get a permanent storage of carbon dioxide in this product. And that, again, is a sort of a removal that acts as a negative on the overall carbon footprint. So these two things together deliver something on the order of an 80% reduction in overall emissions. About a third of that's coming from the removal or the curing with CO2, 2/3 from the change in the embodied materials. All right. Let me show this to you, sort of how it works in practice. And I'm going to do this by using a concrete block plant as an illustration of the process here. And so where I mentioned precast, the technology is broadly applicable to most of the precast market. We're starting in masonry and concrete block in particular. So just a level set here, concrete blocks, like most precast products, are produced by taking mostly sand with some rock and Portland cement. mixing those together, forming them in molds and compacting them. And then those products are moved into curing chambers where the hydration of Portland cement, which is the core reaction that's taking place, is, or the core set of reactions, is accelerated through high temperature and humidity. Okay, and in some cases, producers have started to add fly ash or slag to their mix. That's done both historically it was done to reduce cost, but certainly today it also has the impact of reducing carbon footprint. In this case, the calcium hydroxide that is evolved in the hydration of Portland cement is further reacted with fly ash, for example, to make more of the CSH glue that is really the core piece of the binder in concrete. So when we switch over to our process, that's again happening in sort of at the front and the back end of the process. The first thing we do is change those materials. So I mentioned the 60 to 80% reduction in the amount of Portland cement that's used. We substitute for that in two ways. The first thing we're doing is we're adding a new material called Portlandite, otherwise known as hydrated lime or calcium hydroxide. This is a commodity chemical today. It traditionally is made from limestone. It's made similar ways to Portland cement in that it's heated in a kiln. It's got a slightly better carbon footprint, all other things being equal, because the temperatures it's produced at are lower. And so this process works with Portlandite that's made in the conventional way. I will say that while our economic and environmental value proposition is still very strong with this commercial Portlandite, it's even better if we use waste Portlandite, which we can get from a number of sources. In the future, we anticipate producing Portlandite from calcium-containing wastes. This is the process we have under development. We're not going to use it to start commercialization, but hope to have that contributing our supply in the coming years. I should note this is not a one-for-one replacement with cement. So I said we reduced Portland cement by 70%. We're adding in some Portlandite, but the bulk of the gap is filled by adding fly ash or slag, whatever low-cost waste materials the producer has access to today. And this is really what drives the cost reduction and the reduction in embodied carbon, particularly if we're using commercially available Portlandite. So that's the change on the material side of things. Second step of the process does not change at all. We're producing blocks the same way. Mixing, formation, compaction all happens identical using the same processes. But the second change of the process, I said, is on the back end, where we are curing not just with steam, but also with CO2. So first I'll say the steam curing that happens here is a shortened steam curing cycle. We have less Portland cement in the mix, so we need less steam to get the hydration going. But then following the hydration with steam, we're curing with CO2. And as I said, there's sort of three differences relative to what others have tried before that makes our process low cost. The first is that we can use dilute CO2. So we don't need concentration, we don't need purification. Ideally, we're using flue gas from any number of sources, including biomass. Eventually, the plan here is to get that CO2 from direct air capture. Because our process can use dilute CO2, we can bring down the cost of direct air capture for some of the technologies relative to the requirement for concentrated CO2. Beyond the concentration, importantly, we can do this at ambient pressure and at low temperature. And that means that this process of CO2 curing can be added with low cost, okay? Let me make a couple of comments here about the chemistry of what we're doing. So it's important to say that instead of one or two curing chemistries, as you would have if you were using Portland cement, maybe with fly ash, when you add our technology in, you have three different chemistries happening in the curing process. You still have cement hydration. This is happening over hours and days. So you have early strength starting immediately during the curing process, but there's strength that evolves over a month, let's say. And in addition to the CSH products, which are the main products of hydrating cement, you also get lots of calcium hydroxide. Again, this is sort of evolved Portlandite in the hydration process. Typically, that's what fly ash can take advantage of. So fly ash combines with the ingredients in fly ash, or the components of fly ash combine with this evolved calcium hydroxide over days and weeks. So this is a much longer process to form more of the CSH products that deliver concrete strength. Okay, so to that process, we are adding Portlandite carbonation. Okay, and it's important to note here that everything we're talking about is happening during the curing process. Okay, so this is very distinct from the long duration carbonation that many of you may be familiar with, that happens over decades, where residual calcium hydroxide in concrete reacts with ambient air, the CO2 in ambient air, right? That's a very slow process, creates very little, sort of converts very little of the calcium hydroxide, and it happens over long periods of time. Here we're talking about reacting CO2 at elevated, but not pure, right? Elevated concentrations over a matter of hours to create lots of calcium carbonate, which delivers strength. All right. So with that, let me tell you a little bit about our journey as a company. Let me just do a little time check here. So as I mentioned at the start, the company is born out of research at UCLA's Institute for Carbon Management. And for the first 4 years of work, this is sort of classic academic research. In 2018, the team was fortunate to secure funding from the Department of Energy to scale the process up and run some pilot demonstrations at a couple of test facilities. So the first one of those occurred last summer at a coal plant in Wyoming, where we cured 10,000 concrete blocks using the flue gas from a coal plant. Earlier this year, we moved that equipment to Alabama, and we're able to produce another 5,000 blocks using flue gas from both a natural gas plant and a coal plant. Through that process, we were able to not only demonstrate the process at scale, but develop a system design for commercial, sort of fully commercial plant. We had third parties conduct economic analyses and life cycle analysis. To Lucas's point earlier, this was also the finals for the X Prize competition, which we were excited. After 5 years of work, it was a great way to end that journey with that victory. So that's kind of put us in the position we're in now, which is to start commercialization on concrete block. I'll show you some pictures of those demonstrations in a second. Moving forward, our development work is focused on expanding the product portfolio to things other than blocks, so floor slabs, wall slabs, retaining walls, pipes, right? And then we'll move into harder and harder precast elements as time goes on. We've got significant funding from the Department of Energy to do that. In parallel, we continue to work to push CO2 penetration higher and continue to reduce energy consumption. On the CO2 penetration side, what we've demonstrated to date is concrete blocks that, when finished, 2% of the mass of those blocks is from the CO2 that's reacted with calcium hydroxide to form calcium carbonate. We believe we can over time get that up to about 5%, but 2% is enough to get us going commercially. All right. Some pictures of those demos just to make this a little more real for everyone. So these are pictures from our first demonstration in Wyoming last summer. I won't go through the details here other than to say we were, as noted, we were taking flue gas in directly from the coal plant, using it to cure blocks that had been produced and had a little bit of steam curing done at a partner site, and then but at that point did not meet the specification. And then we completed the curing with carbon dioxide and achieved the specifications that were required. Similarly, as I said, earlier this year, we had the opportunity to run some pilot runs in a more humid environment. We happen to get some ice storms in as well, which we didn't expect in the south, and tornadoes, but all sort of demonstrating the robustness of the process. All these blocks have been donated to various community organizations, and we're looking forward to having those sort of in homes that we can showcase, homes and buildings, later this year. All right. Let me say a little bit about, I've talked about no compromise performance. So let me just talk a little bit about what that means. It's been really important for our team from the beginning to deliver a product that, is concrete block, is not something that's different from a performance standpoint. So first and foremost, the specification here that matters is ASTM C90, and we've had testing performed by multiple labs, both at the National Concrete Manufacturers Association and then Master Builders construction chemicals on the core attributes like compressive strength, water absorption, dimensional accuracy, our ability to tailor weight and density to produce a similar product to what folks are making today. But beyond that, we've also gone through the process of putting together acceptance criteria, draft and code compliance reports with ICCES, which is the International Code Compliance organization. We've also had lots of additional testing performed by NCMA on other attributes that are important as these products move out into the field. Importantly, from an appearance standpoint, we could use the same admixtures that are used today for efflorescence control, for when these blocks are going to be used in more architectural settings. The color of the product is very similar, and like regular concrete, it can be a little bit lighter or a little bit darker depending on what exact components are going in. We got some testing that's yet to be complete around the thermal properties and fire resistance, but given that the aggregate types and fractions are remaining the same, from a chemistry standpoint, we have no reason to be concerned about these tests. Say a couple things about how we're going to market on this. This is a picture that shows how we integrate into a conventional block plant. I think that's important to note here. We don't intend to be standing up our own factories to produce concrete block. There's plenty of infrastructure in this in the West to make these kind of products, whether it's block or precast. And because of the low cost nature of what we do, we can retrofit existing block plants fairly inexpensively. And so that involves some, at the most intensive end, what we're doing is putting in some processing equipment for the CO2, and then making sure it can be distributed effectively throughout the existing curing chambers. All right, I want to talk a little bit about our business model here. I'm sure in this forum, we end up talking a lot about sustainability probably, and I'm happy to share sort of life cycle analysis, et cetera, at a later date. But I think one of the challenges in building materials more broadly has been, how do we get conservative industries to adopt products, right? And I think important for us has been this notion of not wanting to go job by job, block by block, right? That's a really hard way to get scale. And so given this is where sort of the importance of low cost and substantial improvements in sustainability come in, right? So our basic model is to make this a really attractive financial opportunity for concrete producers. And because we believe that's actually the way to make this scale, right? Deliver to users a product that is, from their perspective, indistinguishable, but makes more money for the producer. And if we can do that, right, then this is how we get to sort of ubiquity. So how we do that is threefold. So there's three aspects to our value proposition. The first I mentioned comes from the fact that we're using lower cost materials. So concrete, precast concrete in general is cost structure is heavily dominated by the raw materials. So if you can make a 10 to 20% reduction in the raw materials cost, driven by this reduction in cement, you can reduce the overall cost of the product, and that alone is enough to deliver a strong return on the initial capital investment. But our belief here is that this needs more than just a strong return, right? It needs to be a the best return these producers have ever seen, right? That's how you get them to change. And so the thing that allows us to do that is really the fact that in the last 12 to 18 months, third parties are stepping up to purchase carbon removal. And here I'm talking about things that are not offsets, so not the traditional, you substitute for something that's high emissions with something that's low emissions, and you get paid $5, $10, $15 a ton for that. That's a piece of it for sure, this avoidance piece. But more importantly is third parties that are willing to pay orders of magnitude more, right? And so an example here would be our first contract on this is with the financial payments company Stripe, which will be paying us $260 a ton to remove the first 1,000 tons of CO2 from our first plant, right? And that can really change the economics for a concrete producer that's generally been in a low margin business. And so, as I said, these environmental attributes today are translating into not only emissions reductions for the CO2 supplier or product sustainability, but actually a way of fundamentally changing the profit structure for a concrete producer. And it's our belief that that's how we're going to get scale and make change and drive sort of CO2 out of the system. So we're in discussions with a number of block producers in that regard. As soon as we have one in place, then we start reaching out to the architects and structural engineers that are working in and around that plant to start getting product into their hands. The goal is to be in production by mid next year, and look forward to continuing the dialogue as we continue to and through that journey. So, Lucas, with that, I'll turn it over to you. Happy to take questions, of course.
Great. Thanks so much, Rahul. Yeah, we have a little bit of time for Q&A, which I'm excited about, and we may run over the hour just a little bit. So if anyone has to drop off now, we'll just do a little bit of housekeeping, and that is keep an eye out for, there's still a couple healthy materials series that's been going on with SF. We'll drop a link in the chat, and then keep an eye out on the Slack for future events. Okay, Q&A. Would love to. Oh yeah, Laura, do you have anything you want to contribute?
I have one question from the chat that was direct message to me and not to the whole group. So Jill would like to know. Jill's very excited about Rahul's presentation and would like to know when she can spec it for her next project.
Yeah, thanks, Jill. I think as I noted, right, we can't spec anything until we have a producer that's making products. So we'll be working from the production end forward. I guess I would ask, as soon as we've got something in Southern California, I would say this group will be the first to know.
Awesome. So if anyone else has questions, you can definitely drop them into the chat. I guess I will contribute my own question, which is that I noticed that you said you're using fly ash in the product, and that you are also using flue gases from coal and natural gas plants. So what happens when we stop burning fossil fuels?
Yeah, it's an awesome question. So I'll say a couple of things here. I think historically our, the technology development, some of the motivation behind it, certainly some of the funding behind it was sort of coming out of how do we do integration with coal, heavy industry, and frankly, it was before the trajectory for coal was as obvious as it is now, which is good. So I think I would say a couple of things here, right? On the flue gas side, there's lots of different sources for CO2, and I think for us it will be what the vision is direct air capture, right? But direct air capture today is not at a cost point that we need it to be. We have some work going on internally on that front, but there's also lots of other people working on it, and we're happy, whoever can get there fastest into a reasonable cost point is great. We also, we view ourselves as an enabler for direct air capture, because most direct air capture, if you're just getting CO2 and having to put it in the ground, right, there's no, the utilization side of it is a cost, right? Whereas with us, the utilization side becomes a profit. So we think we can enable direct air capture economics, but our choice is wait till direct air capture is there, or to get the utilization technology up and off the ground and commercial and low cost, take it out of being an idea and have it be real. And frankly, we'll use whatever we need to get there. I don't think there's no coal plant that's going to stay open because we put this on. We're not making, if we were to locate at a coal plant, which we will almost certainly not do, you would have to make so much concrete there that you'd then be stuck with, like, how do I distribute this, right? So I think we will concentrate for our streams on things that are hard to decarbonize, and I wouldn't consider coal or natural gas hard to decarbonize, but cement, steel, right? There's other processes that's one category. The second would be biomass. So if we're capturing the CO2 from an ethanol plant or a bioenergy plant, that's, I'm not saying there aren't complications there, but that's still better, obviously. But, this is all sort of basically to get the utilization side of the process to be low risk and proven, so that as direct air capture comes along, we can help with that. Laura, does that answer? I think that answers hopefully answers one of the questions on the CO2 side. On the fly ash side, so one thing I did not talk about is the fact that in addition to being able to use more fly ash or slag than you could typically put in conventional concrete, we're actually able to use sort of lower quality SCMs as well. And that is because generally with flue gas, we're operating at higher temperatures. We also have the heat that's evolved from the carbonation of Portlandite. So you have more heat basically, both from the gas and from that's evolving, and that just unlocks more hydration reactions in the Portland cement and more pozzolanic reactions. So you sort of get more out of worse material. And as I'm sure many people on this call are aware, like we've got billions of tons of off-spec fly ash sitting in landfills in this country, and it'd be great to find ways of getting rid of that.
Yeah, and I see Tarek has
Tarek's
posted
point.
a comment on that in the chat. Thanks, Tarek. Next question is going to be for Rushita. One of the things that I really appreciated about your presentation was the discussion of the system boundaries, and that you got to look at the same project, kind of looking at, okay, how does your system boundary affect your output? How does which EPDs you're choosing affect your output? So for those of us who are busy professionals and don't have time to do an entire thesis for each building we work on, do you have any advice for us or lessons learned for us in practice that you learned from doing this deep dive?
Yeah, I would say, like, for most people, when you talk about timber, they're like, oh, it's a good material because, it sequesters carbon. But then, like, I think for every professional, I think we should carry out an analysis which accounts for it, as well as in a situation where you can't account for it. So you're not like, you don't end up with misleading results or have a wrong footprint for yourself. Yeah, and secondly, yeah, transportation does impact, so to account for that.
That's great.
Yeah, that was a really surprising aspect to me, the transportation piece of that. I have a follow-up question as well. So you recently started working at AECOM. How are you taking your research in the industry and applying this, knowledge?
Yeah, I am doing life cycle analysis over there on projects. So this has been really handy. The whole understanding of embodied carbon and everything, like every other aspect of it. It's been really handy in taking my work forward there.
Great, thanks. Let's see, another question in the chat for Rahul. Are there any regulatory hurdles with a high percentage of SCM use?
Yeah, I mean, I think the specifications are flexible enough that we can make those changes and meet the spec. I think that's probably the best thing I could say there. We have to be thoughtful about it, and it's not a no-brainer. But I think for the range of formulations that we look at, so it's not a single formulation, but what we do is when we talk to a producer, we see what they're using today, and what materials they have access to, and we go from there and design something that's sort of within our overall formulation design space. But in those ranges, we fit within the existing flexibility that's there in the spec. We've added the sort of ICC-ES piece on top of that, just to sort of be, make absolutely sure that if someone's concerned about an issue, we've got that as well. But yeah, our read of the spec is that we've tried very hard to stay within that as we've considered the options we have. And that's not a technical issue. It's just a practical reality that if you need to start changing specifications, both for a startup and just overall timeline, that adds a whole new dimension to things. Right?
Great, thanks. And I think Jill just shared another article in the chat regarding the fly ash issue, if you guys want to check that out. Luke, go ahead.
Yeah, one more question from the chat. Rushita or Rahul, can either of you envision precast concrete elements being produced by CarbonBuilt being incorporated into a hybrid system, CLT or mass timber buildings?
Yeah, I mean, maybe I can start because I know less about this, and Rushita will probably be able to either correct or add to that. But yeah, I mean, to me, I don't see these as mutually exclusive, right? I mean, there's no reason you can't try to find the best elements to achieve the function of whatever piece of the design you're going for. So yeah, I don't see why not there, but I'll let Rushita chime in.
Yeah, I think they can be. So for the case studies that I did, like the composite timber structural systems usually do have precast concrete to carry a big part of the load, because you can't just rely on timber for everything, because that could lead to a lot of organizational rigidity. So yeah, I think it can be used.
Yeah, it seems like a really interesting pairing to me too, of potentially combining that or finding some symbiosis with design for deconstruction as well, and reuse of building materials in the future. One other question. So I have a structural engineering, put on my structural engineer hat for you, Rahul. You mentioned sort of the carbonation process that sometimes referenced for carbon sequestering over a long period of time for concrete. Some things I've read about that is it can lead to corrosion, or it can negatively impact the durability in the rebar. Yeah. What sort of, like, to put the structural engineers at ease, what has CarbonBuilt done to consider this, or is it?
Yeah, no, it's a great question. That's one of the, I think one of the challenges in thinking about this long duration carbonation as a source for CO2. I mean, you'll see this from the cement industry these days, as sort of talking about it as trying to take credit for the long duration carbonation that happens. And I mean, the challenge is that as you remove calcium hydroxide, or it's carbonated, you get a slow drop in pH, right? So it's that sort of more acidic nature that is the problem. In our case, like, it's a very controlled process, right? So we can tailor the process so that when you're done curing, what the calcium hydroxide level is, and sort of you either can have a buffer there if you want one for reinforced product, or if you don't have reinforced product, and obviously like block, for example, right? Most of it is used unreinforced. We can carbonate away all the residual calcium hydroxide, so that's not an issue. So we look at this as a something we can tailor depending on the product, and if it is reinforced, we can, obviously we're adding a lot of calcium hydroxide to start. We can end with a buffer that is suitable for the use of that product, right? If the product is going to be used in a way that's more susceptible to conditions that would lead to that, we can have more calcium hydroxide buffer. And that's going to create more space, right, for that long life carbonation to happen without having the problems, right? On the other hand, if it's not susceptible, we can dial it back, right? So is that helpful?
Very helpful. Yeah, thank you.
So we are at 6:01 now. So I want to thank everybody for joining the call, and I definitely want to thank our presenters. It was really great. I thought it was really great to see these two presentations together, actually, because they're very different perspectives, but that also definitely complement each other. So thank you to both of you, and thank you to everyone who joined. And keep an eye out for our next event, which will be in August.
Yeah, thank you so much for your time, Rushita and Rahul. Really appreciate it.
Yeah, thank you so much.
And
Thank
for the
you.
research. I
Appreciate the
mean, it's really
opportunity.
important work. So it's great. Looking
Thank
forward to hearing more.